Go, trying again. So properties of logarithms, we only got about halfway through our list, but we'll recap the whole list and do some examples. Where the stuff comes in, and it's strange. It's weird. It's like I'm giving a little guide to a treasure map, and you're like, look for the rock. It looks like an elephant, and it's like doesn't make any sense until you get into it and start working on it, right? So our first one was this translation, right? That translation was b to the x equals y is equivalent to log base b of y equals x. When in doubt, try it, right? If you're having trouble with something, you're trying it. Certainly, if it looks like a log function, you could convert it to exponential, and maybe it's easier. What's up, Ben?
That was an accident. I'm sorry.
Oh, no problem. No problem. I just when I see the yellow come on the outside of the your individual frames, I know your mic is live, and I want to just make sure you get things answered. Just taking attendance real quick. So our first one is the translation. Then we had the product and quotient. Right? And I said log base b of m times n is log base b of m plus log base b of n. And that proof is in the book and in the lecture, right? So Ben, you should know these proofs of all these. And if after you see me prove that first one, you should be able to do the next one in the exact same way. What's my thought on this one? What did I ask you to have a thought about on this particular property?
Yeah, we should think of it as adding an exponent.
Exactly. So when you're multiplying like bases, you add the exponents. Exactly. And so the next one is very similar. I'm going to be dividing. And what am I doing with exponents there? I'm going to be subtracting, right? And the real weird thing about these is we have to be able to not only go from left to right, but also go from right to left, right? If they give me something contracted with a single log, I should be able to expand it to multiple logs. And if they give me something expanded, multiple logs, I should be able to contract it down to a single log, right? And the next one is log base b of m raised to the n. That exponent becomes the coefficient. Now that one I didn't prove. I'm going to do a pseudo proof of it here. I'm going to demonstrate to you that it should really make obvious sense, right? So, but I don't want to confuse this with this is my first property. These are my next three, right? And I think I have 5 more to do today. And yes, they should be in front of you when you're doing these problems. Right? Because you're saying, well, let me hunt for this treasure. Let me look for the pattern. Oh, this one looks like this property. Maybe I can try this property, right? So kind of a pseudo proof of star is I would just look at log of x squared, right? And log of x squared is log of x times x. And now I can go to my first property, which is log of x plus log of x. And you see how many of those do I have? I have 2 of them. So you can really see how that exponent comes out as a coefficient, right? That's not a proof. There's a proof of this in the book, but it should kind of convince you that it seems to work, right? That you can see that x squared, that 2 is coming out front as the multiple, just using previous properties. my next property that I want to talk about are the inverse properties. So we just go through this list, and then we will do a couple of example problems, see how we can apply them, and then you'll really see where they're valuable when we start doing actual problems from the from 5-6. I don't have to lecture on 5-6. We're just going right into solving equations. So inverse properties are b to the log base b of x is equal to x, and log base b of b to the x is x. So I kind of want us to see that if I compose two inverse functions together, the functions all disappear, and all I'm left with is the input, right? So these are both really easy to see if I just use my translation. So somebody translate this first one to me. What's the first one? First of all, is the form I'm showing exponential or is it logarithmic? What's the main function here? What's the outside function, the one in control?
Log b of x.
Exactly. So I want to turn this one into a log function with my argument, right? Is that true? Don't tell me. Give me a second. Well, let me do the second one first. What's the base? All right, fine, I'll just answer it. B. What's the exponent?
Right.
Good. What's the argument? What's the interior function?
C to the x.
Okay, obviously true. B to the x equals B to the x, right? All right, next one. I want to turn it into a log function. So it's log base what? What's the base?
B.
B. Log base B of
X.
x, right, should equal the exponent. Log base B of x, obvious. So just to, but you know, these are just the demonstration that it has to be true. These are my properties. If I have, and look at where my x's are. My x is in an exponent, or my x is locked inside of a log function. To get it out, I need to use the inverse. Here, my x is as an exponent. To get it down as a coefficient, I need to use the inverse properties, right? And we'll use those quite a bit today. Finally, change of base. It says that log base b of x is the log of x over the log of b, or the ln of x over the ln of b. So, and these two I have on my calculator. Actually, I have log base b on my calculator as well. It's just hidden inside the math functions. But I want you to be able to show me the work, the algebraic work anyway. So those are my last three properties there. And of course, this one is easy to show. So log base 2 of 8. What exponent makes 2 into 8?
3.
Yep.
3.
So do, on your calculators now for me, do log of 8 over log of 2. And do ln of 8. Make sure you close your parenthesis over ln of 2. And all of them will give you 3. Do that on your calculator, please. Yep. Yes. Nice. Good, let's do some problems from the textbook. Just have to log in real quick. I opened the textbook through MyMathLab. It lets me see the whole book instead of just sections of it. And then I'll just encourage you to take a couple of photos of this page I'm showing today, so you can do problems from the textbook. Oh my God, it's so slow. Drives me crazy. Nice. So I'm looking at the homework problems in 5.5 here. I don't know why I can't fit the whole damn book on the page. It's so stupid. So, but starting at 12, we've got our basics of what's going on. I don't really see us doing many problems like this because these things happen inside of our 5-6 problems. Okay, so but again, they might be asking you expand a single log into multiple logs or contract multiple logs into a single log. So like right now we could do number 49. I think all of these are good to do. Number 37 up to 70. If you want to get a picture of these. Why can't I zoom a little bit better? Fit to width. Just doesn't quite fit, and I can't zoom it. It's so stupid. Ugh. Anyway, 45, 37 and on are pretty good. I'll try and give a couple of windows here. To show this. Let's do 49. So 49, if you remember, your third question on the test is for you to find the domain of a log function. Sorry, second question. Find the domain of a log function using a sign table, right? And so this one is saying, I don't care about the sign table. I'm only going to just give you a simple domain just so that everything stays positive inside. For sure, I know everything is positive, right? So I'd have to do a sign table with 0 and 3. So I'd have to be checking left of 0, in between 0 and 3, and bigger than 3, right? Can you see the critical values of 0 and 3 here? So, yeah. And we will do one more like that today, okay? So log base 2 of x cubed all over x minus 3. I want to expand this, right? So this is 5.5, number 49. My pen is freaking out. I've got log base 2 of, was it x cubed over x minus 3? Let me just double check. Yeah, x cubed So I see that I'm dividing in the argument, so I'm going to turn that into 2 logs, which I'm subtracting, right? So this is log base 2 of x cubed minus log base 2 of x minus 3. So I'm just kind of looking at my list and saying, well, what can I do? And it wants my arguments to be linear. It wants to be log of x or log of x plus b, right? It wants to be an mx plus b inside the argument, so I just have to get this 3 out of here. Log base 2 of x minus log base 2 of x minus 3. And that's all I can do. Pretty simple. Seems to have no purpose at all, but you'll see where the purpose comes in when we do 5-6 today. Okay? So just trust me on it. Practice expanding, practice contracting. Let's look at that one with the contraction. So I guess 63 is fine. Let's do 63. Again, you can take a picture of this if you want to right now. The ones in my Math Excel are just a little bit simple. And then if I give you one, well, I'm not giving you anything like this on the test, but it will happen inside of the solving equations. Okay? So 63, right? So I've got the ln of x over x minus 1 plus the ln of x plus 1 over x minus the ln of x squared minus 1. Well, I see that I'm adding 2 logs here, so I can use that one property there where I'm multiplying the arguments, right? So I've got the ln of x over x minus 1 times x plus 1 over x. That simplifies a little bit, so I certainly can simplify that. I can cancel those, and so I have this problem now. ln of x plus 1 over x minus 1. I'm sorry about my pen. It's probably my computer just freaking out, memory-wise. Is it okay on your side? Is it really blurry, or?
No.
Okay. Now when I'm subtracting 2 logs with the same base, and these are log base e, I can combine them into a single log by dividing, right? X plus 1 over x minus 1, all divided by x squared minus 1. And of course I've got a keep, change, flip problem there, right? Keep the first fraction, change my divide to times, and flip the second fraction, right? So we're talking about the ln of x plus 1 over x minus 1 times 1 over x squared minus 1. Right? That last one is really something over 1, and I'm doing keep, change, flip, flipping that second fraction. This does expand, right? I can do something with this. I've got x plus 1 over x minus 1 times x plus 1, x minus 1. And I can see there, is everybody okay here? Don't let me go too fast. I can see here that my x plus 1s will cancel. And I have the ln of 1 over x minus 1 quantity squared. It's almost exactly what I want, and it certainly would be 9 out of 10 if you did it. But we want the ln of a linear inside. So I can see that I can change this x minus 1 to the minus 2, right? That just simply means reciprocal. And then I can use my property that this negative 2 will come out. and I'll get the negative 2 times the ln of x minus 1. And I'm trying to get down to a linear argument of a log function. Right? Is that making sense what I'm saying? I want this piece in here to be an mx plus b. And there's my final answer. So it's just a lot of using the properties, doing some algebra, trying to, use whatever you can algebraically to get it to be some coefficient times the log of a linear. How we doing? So I think you can get a better photo of the right-hand side here where you have to expand. So if you're taking photos, take a photo, please. And then the right-hand side of these problems where you have to contract. You have to take the expanded logs and bring them back to 1. And again, doesn't seem to make a lot of sense or have any purpose until you see the next section. And then finally, a change of base formula to do. This is essential. So you can take a photo of these problems here, 71, 72, 73. I think I can get all of them in on one page here. Nope. So I like all of these up to 85, 84. So there's the rest of the picture if you want it. So let's just do 71, log base 3 of 21. This is 5.5, number 71. Log base 3 of 21. Now there is a way for me to get this in my calculator. If you go into the math menu and then the functions menu, you'll see a log base b, but it's easier just to turn it into a change of base. So this would be the same as ln of 21 over to ln of 3, or log of 21 over to log of 3. So get me a decimal there. So 2.7712434749. So x is a nice maybe 2.8, 2.77. I don't care what you round.
Professor, how many decimal places do you usually want us to round up to?
I don't care. Like, I'm not an engineer. All of you that will be engineers, you're going to have to approximate. I don't have to. I like the definite answer or exact answer. Right? This is my exact answer. This is my exact answer. This is my exact answer. And this is my approximate answer. So whenever I did it, I would just write out as much as my calculator would give me and then round to wherever I thought was appropriate.
Got it.
I mean, for me, it's usually money, so 2 places, but I don't care. If you don't get the exact answer right, your approximation won't be right. And I care more about the exact answer. And this is why we have all of these things built into bridges and buildings to allow sway or expansion of materials, because you can't do it exact anyway, right? So you got to have all these little fixes in to allow things to not be perfect, which is kind of scary, but nice. We're ready to move on to 5.6. And so 5.6, I can see 2 problems coming from here. I can see me having you solve a log equation or solving an exponential equation. Okay, so let's take a look at the most famous exponential equation, and then we'll do one at the level that I expect you to be able to do. Okay. So, and we have to go to the book to get better example problems than what I put on Math Excel. Do Math Excel, and then get to the ones in the book that I want you to do, right? So we know what 2 to the second is, that's 4. And we know what 2 to the third is, that's 8. So, but what if I wanted 2 to the x equal to 5? What could you say to me first? Where do you think that x is? Right, 2 squared is 4, 2 cubed is 8. If I want 2 to some power to equal to 5, it's got to be between 2 and 3. And if I think about, you know, the logarithmic function, right, 1, 2, 3, look at how little change there is. Look at how straight that tangent line looks there. I'm thinking it really behaves somewhat like a linear function there, right? Do you see what I'm saying? That the arc is not real steep there on the log function. It's almost straight at that point. In fact, it just keeps getting straighter and straighter as it goes on. So my x should be really closer to 2 than 3, right? Because it almost behaves linear. Because 5 is closer to 4 than 8, right? So we're going to do this a couple of ways. The way to start is, and I prefer to always use ln, but we're going to start using an inverse function, so log base what?
2.
Yep, log base 2. I'm going to take log base 2, both sides. And so why am I allowed to do that?
Because they have the same basis.
Nice. I would agree with that. I would go a little bit further back and say because they're one-to-one. When you have one-to-one functions, you can compose them with one-to-one functions and not lose equality. So whether I take the ln of both sides or raise both sides to base e or etc., because I'm starting with something equal and I'm using a one-to-one function, right, as my composition, I keep the equality. If I was using non-one-to-one functions, I don't. Okay. So, so what happens on the left? Log base 2 of 2 to the x. Well, I could do this a couple ways. I could just know that log base 2 and 2 to the x are inverse of each other, so I just get x, right? So there's my answer. There's my exact answer, right? That's it. That's my exact answer. To go to my calculator, I can use my change of base. So x equals the ln of 5 over ln of 2. Or there's an exact answer, or log of 5 over log of 2. And so now let's get an approximate. I don't need to do both because they're both going to give me the same answer. So log of 5 divided by log of 2. I get 2.321928.095. Anybody else? Yeah? Now, I want to do the same problem the way that I would normally do the problem, and that is using the ln function. I don't like writing log base 2, that's 4 characters. I don't like writing log, that's 3 characters. I like writing ln, 2 characters. So I'm going to do the same problem. I've got 2 to the x equals 5. I'm going to take the ln of both sides. What happens to that x?
Goes down.
Yep, so I get x times the ln of 2 equals the ln of 5. So I get x equals ln of 5 over ln of 2. Same answer. I would like to be able to write it as an exact answer. As an exact answer with one log function or an approximation, right? So an exact answer with one log and as an approximation. So if you're always starting with an ln, you're going to end up with something in my double box here. And then you can convert it to change of base. You can use the ln piece as to get your approximation. So let's do a problem like this at the level I want you to do on the exam. So let me show the book. For section 5.6. So questions 5 to 40 are log equations. I'm going to give you one of those. And questions 41 to 55 are exponential equations. I'm going to give you one of those. Let's do number 50 here. If you want to get a quick picture of that, and then a quick picture of this. So I can't get all of the section on the one screen, so I don't know why. So a picture there, and a picture here. So I've got 5.6, number 50. I've got 2 to the x plus 1 equal to 5 to the 1 minus 2x. And you'll see the algebra here is going to be just like the algebra for finding the inverse. So that's good in the sense that if you can find the inverse function, you've got exactly the algebra skills you need to be able to find this solution. Okay. So what would be a good log function to use? ln is what I'm going to use, but it's certainly log base 2 or log base 5 would be fine, right? And of course log works as well, but I'm just going to go right to the ln. Now I'm using my property that exponent can come down, right? If I have an argument with an exponent for a log function, I can bring that piece down. And in this case, I have to be careful with the multi-term. So x plus 1 in parentheses times the ln of 2 equals 1 minus 2x, that quantity times the ln of 5. How are we doing? Remember, I'm trying to solve for x, and if you can remember, I had to get rid of parentheses because I want to gather all my x terms on one side. So I'm going to distribute here, right? I get x ln of 2 plus 1 ln of 2 equals 1 ln of 5 minus 2x ln of 5. Everyone okay here? I want to gather my x terms on one side with the minimum number of negatives. If I move my x terms to the right, I'd end up creating three negative terms. It's not wrong to have that. It just takes a little more factoring at the end. So if I move my x terms to the right, I notice I'm only going to have one negative term. So I get x ln of 2 plus 2x ln of 5 equals ln of 5 minus the ln of 2. Is everybody with me there? Jamal, 10 to 11. Tuesdays and Thursdays I have 10 to 11. Monday, Wednesday, Friday I have 9:30. No, sorry, yeah, 10:30 to 12. Everybody with me?
Got it.
Nice. So I got an x I can factor out. I got the ln of 2 plus 2 ln of 5. And on the other side, I can see I can contract. Got an ln of 5 minus an ln of 2. That's an ln of 5 over 2. How we doing? We okay? 2 ln of 5 is I can do that one little property in reverse. That's ln of 5 squared. Right? And 5 squared is 25. And of course, I'm adding two ln's there, right? So I can use that product property and say I get x times the ln of 50, and that's equal to the ln of 5 halves. ln of 50 is just a number, so I'm going to divide by it. I get x equals ln of 5 halves over the ln of 50. That's an exact answer. It's not horrible. I can use a change of base here. I would like to use a change of base here. So I get x equals log base 50 of 5 halves. So that's the nicest, most compact way I can write an exact answer. So I like an exact answer with ln's, an exact answer with a single log, and then finally an approximate answer. And I'm going to use my ln version to get the approximate answer, right? ln of 5 halves divided by ln of 50. 0.23422422698. X is approximately 0.2. Sorry about the pen. Probably my battery. So exponential equation, getting me an exact answer with ln, getting me an exact answer with a single log, getting me an approximate answer, right? So practice a bunch of those. I'll try and do one every class until we take our test. Good, so that starts with an exponential problem. Let's look at ones with a log. So solving a log equation. So number 17 to 40 here are pretty good. So if you want to get a picture of that right now, and then I'll slide over and get a picture of the right-hand side. Now what's weird in these problems, what happens is I sometimes will get an extraneous answer. So I want to make sure when I'm solving these that I'm plugging my x values I get back into the calculator, right? I want to make sure that I always check my answers and make sure there's no conflict in the original problem. So let's take a look at I don't know, 21. So I've got log base 2 of x plus 7 plus log base 2 of x plus 8 going to be equal to 2. Well, on the left-hand side, I certainly see one of my properties. I can combine these two logs into a single log with an argument of a product, right? I get log base 2 of x plus 7 times x plus 8. It's always kind of hard to tell the argument there when you have multiple products, so I just try and make it real clear where the inside part of that function is. And now if I could get rid of the log, it would be perfect, right? So I have to raise both sides base 2. So 2 to the log base 2 of x plus 7 times x plus 8 is equal to 2 squared. I'll see students often raise one side to base 2, but not the other side base 2. So you got to be careful of that. What you do to one side, you do to the other, right? And we've been saying that a long time, because multiplication is one to one, division is 1 to 1, adding is 1 to 1, subtracting is 1 to 1. We're doing all of this stuff because these functions are 1 to 1. What you do to one side, you do to the other, right? So raise both sides base 2. What happens to 2 log base 2? Their inverses, they cancel. So I get x plus 7 times x plus 8 is equal to 4. And now I'm back in 8th grade or 9th grade, or if you were like me, 10th grade and 11th grade, and just going to solve a quadratic here. So I get x squared plus 15x plus 56 equals 4. So I get x squared plus 15x plus 52 equals 0. And I'm just trying to find a product of 52 that adds to 15. I don't know if I can think of it in my head. So 52 is 1 times 52, 2 times 26. Does 3 go in? No. 4 go in, yes. 4 times 13. 5 go in, no. 6 go in. Did I make a mistake somewhere? Anybody see a mistake? They usually give you things that are factorable. That's why I think I made a mistake. Did I write the problem down wrong? Well, it's fine because I can just go to my quadratic formula. No. Oh, yes I did. Damn it. It's equals 1. Stupid hard. So this is a 2. And this is a 54. And it's 6 and 9, right? 6 times 9 is 54. 6 plus 9 is 8. So I get x plus 6 times x plus 9 equals 0. So x equals negative 6 or x equals negative 9. Now these are my answers, but I don't know if they work yet. I have to make sure I check them in my original problem. And you can see one of them is going to not work out. Which one doesn't work out when I put it in? when I put in the answer to the x's, what happens?
-9.
The -9 is no good, right? So we call this guy an extraneous solution. It almost looks like heinous and extra. It's an extra solution that's just bad. Right, if I put that in, log base 2 of -9 plus 7, right, plus log base 2 of -9 plus 8, I get the log of two negatives, and I can't. The argument of a log function must be positive. Right, I get log base 2 of -2. No good. Right, this is no good. So I want to make sure I put both my solutions in and make sure they work. Okay. Nice. Yes, because remember the log has a domain of a positive number, right? So I like to think of, here's my xy axis, here's my log function, right? I can see that I can only put positives into that. So I'll just think of this as log base b of x, right? In my particular case, I have log base 2 of what, x plus 7? That means I'm moving this thing 7 to the left, right? So, and in that particular case, I can see that I can put anything bigger than -7 in. So the -9 fails. Let's do another one of those. Uh, 32 looks fine. Let's do 32. So I've got log base a of x plus log base a of x minus 2 equals log base a of x plus 4. Well, the only thing I really see is left-hand side. I'm adding two log functions, so I can create that. I can write that as one log function as a product, right? So I get log base a of x times x minus 2 equals log base a of x plus 4. And at this point, I realize I have one-to-one functions. So I've got two equal y values here, right? I've got two equal y values, which means what's got to be true about the interiors. Since my exteriors are equal and it's a one-to-one function, my interiors have to be equal. So I get x times x minus 2 has got to be equal to x plus 4. And I'm back in 9th grade. I've got a quadratic again. X squared minus 2x minus x minus 4 equals 0. Don't let me go too fast, everybody, okay? So I've got x squared minus 3x minus 4 equals 0. I need two integers that multiply to -4 and add to -3. That's -4 and positive 1. So I get solutions of x equals 4 or x equals -1. Those are my initial guesses at answers, but I have to check them in the original equation to make sure something's not extraneous. And it's pretty clear which one is extraneous. The 4 is no problem. It's the -1 that for sure fails, right? Now, I should still check the 4, right? You want to walk out of this test knowing you got this one right. So I want to check that 4 anyway. I already know the -1 works for a domain issue, fails for a domain issue. But the 4 I should still check. I get log base A of 4 plus log base A of 4 minus 2 equals log base A 4 plus 4. Okay, well I get an 8 on the other side. On the left-hand side I get log base A of 4 plus log base A of 2. Well, all right, if I multiply those arguments, I do get 8, right? So I got it right. Log base A of 8 equals log base A of 8. Check. Nice. All right, this is it for chapter 5 for us. Like 2 questions from that section. One where you have a log equation you got to solve, and one where you have an exponential equation where you have to solve, right? So that means we have 5 questions already for the next test, right? Show a function's one-to-one, find the inverse, do the composition to prove it. Get the domain of a log function using a sine table. Solve a log equation, solve an exponential equation, and do a difference quotient with the secant line. Eventually, you're gonna show me you can do this stuff, or you can't, right? I'm gonna just keep showing you the same stuff until you can do it, because guess what? You do it over and over in Calc 1. All right, let's do a domain for a log function and then quit for today. Right? So find the domain using a sine table. And I'll say f of x is the ln of x cubed minus 1 over x squared minus 3x minus 4. So what is our main argument is we want to make sure that the interior function is positive, right? So g of x equal to x cubed minus 1 over x squared minus 3x minus 4. I need g of x to be greater than 0. Right? Whatever I'm putting into that log function has to be a positive. I can't put a 0 in, I can't put a negative in. So I'm going to split up the number line and see where my g of x function is above ground. Right? Everybody with me here? Nice. So I got a factor. I get x minus 1 times x squared plus x plus 1 over x minus 4x plus 1. Does anybody need to see the factoring there?
Yes, please.
So the downstairs one we did already today, right? I'm just looking for integers that multiply to -4 and add to -3, right? So we had that one already. The other one, I can see that 1 is a 0, so I'll synthetic divide with 1 cubed, 0x squared, 0x, and minus 1. And I get a 1, 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 I get a 0. And you can see my x squared plus x plus 1 there. I'm going to try and sneak synthetic division on test 3. I don't know how I can do it yet. Most likely will be in this problem. I got my critical values. Of -1, +1, +4. I know for sure that x squared plus x plus 1 is never greater than 0, right? So there's no roots to that. The roots are complex. So the only critical values, the only time the numerator or denominator are 0 at those 3 values. And of course I could do this from the graph. So now I've got critical values of -1 can't be used, 1 can't be used, 4 can't be used. So I'm thinking about those pieces on my number line. And those are going to create my column separators. And my row separators are going to come from my factors. I have 4 factors. I've got an x minus 1, an x squared plus x plus 1, an x minus 4, and an x plus 1. How is everybody doing? I mean, it sucks it takes so long to do these, but you'll thank me when you do first derivative test, second derivative test in Calc 1, sorry. So we need test values left of, right of, and in between each critical. So I'll pick -2, I'll pick 0, I'll pick 2, I'll pick 5. Anything I want left of, right of, and in between. So I'm looking for where g of x is positive, right? So I'm going to plug my test value into each of my factors and see what kind of sign I get out. I get negative, positive, negative, negative. 3 negatives is going to give me a negative. So this piece I don't want. It's no good for me. I can't let a number go into my function that's less than -1. It will then give me the ln of a negative, and I can't do it. Everybody with me here? I only have 2 people saying yes. Thank you. 4, Thuria, Wilder, Elmer, Elise, Ryan, Jamal, thank you. Cindy, thank you. Ben, thank you. Amir, Oscar, Manish, Abraham, Yvonne, Sarah, Surya.
I'm getting most of it. I'm just going to have to practice some more.
Yes.
That's mainly it right now.
Yes, agreed. And you can go onto YouTube and watch any nerd do a search for pre-calculus sine table radical inequality. Sorry, not radical, rational inequality. When I plug into 0, I get a negative, I get a positive, I get a negative, I get a positive. I've got an even number of negatives. That will give me a positive result out of the function g of x. An odd number of negatives will give me a negative. An even number of negatives will give me a positive. So I already know I want the interval from -1 to 1 for sure in my domain, right? Because that gave me a positive. That's what I'm looking for. When I plug the 2 in, I get a positive, positive, negative, positive. So that's a negative. I don't want that piece. And when I plug the 5 in, I get all positives. And of course, I'm going to get a positive out of that, which means I want that interval as well, 4 to infinity. So the domain of f of x equal to the ln of x cubed minus 1 all over x squared minus 3x minus 4 is -1 to 1 union 4 to infinity. Now, you can cheat this. You can cheat the whole thing, right? You can just graph it. And when I graph it, I'm not only going to graph my original function, I'm going to graph my interior function so I can understand what's going on here. So let's go to Desmos. So I've got y equals the ln of x cubed minus 1 all divided by x squared minus 3x minus 4. And I can see where my function exists, the x value, the shadow on the x is the domain. And I'll make it a little bit easier to see. Well, you should be able to see between minus 1 and 1 and bigger than 4, for sure. Right? Between minus 1 and 1, I have my ln function, and bigger than 4, I have my ln function. Now, what's interesting is to take the inside and graph that. And remember what we want the inside to do. We want the inside to be bigger than 0. So we're looking to see if the places that match up with my red curve have a piece of blue curve that's above ground. So notice on the left, I got a piece of the blue curve that's underground, and there's no red curve there. The ln doesn't exist there because g of x is negative there, right? You can see g of x coming down until it hits the x-axis on this middle part right here. Can you see my mouse? You can see my mouse moving, right? So it hits 0 right at 1 and then goes underground, and then the red curve disappears from there. And then here's my blue curve, bigger than 4, above ground. That's why the red curve exists there. Where g of x is above ground, ln of x will exist. Well, we got good news.